Oops.
Hello? Hello? Can you hear me?
Yeah, we can hear you.
Okay. Need louder or it's okay?
I think you're good.
Okay, thank you. How's life?
Doing all right.
Hanging in there.
Okay, I will stop the video for the quality. Okay. Can you see the slides and others?
Yeah, we can.
Okay, okay. Right now we have 20 students. So while we have 56 students are not here. Yeah, let's go. Let's go. I have updated the syllabus. I sent out the email. Have you noticed?
I haven't checked it out yet.
I made some changes. For the assignments, we have 9 assignments in total. So students can drop one lowest score when we calculating the weighted total. And second, the final project. The final project is no longer teamwork. So I will reduce the workload of the final project and post the project this week, tomorrow. For the quiz, so we have no quizzes anymore. And the weight assigned to the quiz is not changed anymore also, keeping as 5%. Still, you can drop off one lowest score. Exam two will be open textbook exam. So you will have 1 day. Remember, you have 1 day, April 16th, to solve all the problems and scan upload your solution to the blackboard. And I have to emphasize that any cheat that is, if I find any cheat, that will be a F. So exam three is a final exam, right? So it's also an open textbook exam. So you will have work on I think we did not receive any email from the university side. So, but I guess it will be on the scheduled at the beginning of this semester, May 15th. And but it's a open textbook exam because I cannot force you to open the textbook, right? So for this, do you have any questions?
Sounds good.
Okay.
Yeah, no questions.
Okay. And for the middle term, we have statistics. The grade distribution is here. Can you see? Here, we have 16 students got A, and 32 students got B within 80 to 89, and 19 students got C. So 4 students got D, and 5 students got F. So for the distribution is very excellent. But for some students, that is the performance is not good. So I encourage all of you to try to input more effort and do the assignments, labs, and projects, and read the materials. Try your best to catch up. Okay. So if you don't have any new questions, then we go to the slides. It's clear? Can you see the slides here?
Yep.
Yeah, you're good.
Yes.
Okay, okay. So last time we talked about the conditional branches, or you can say how to change the sequence of the instructions. Because in the fetch phase of executing an instruction, we always increment the PC by 1. Do you remember? So this means the instruction is executed actually in sequence 1 by 1, following the sequence. So it is possible for us to change the execution sequence, like the high-level programming languages. They have loops, if and then, or function call, iterative, right? So for these, can we do it? The answer actually is yes. Last time we have a lab, right? So, but it needs the special instructions. So to change the PC, the value stored at the PC register. So for these instructions, actually are called control instructions. We have 3 types of control instructions. One is called conditional branch, DR. For this one is, If some condition is satisfied, then one branch is taken. If not, the PC will point into the next sequential instruction. So the second type is called unconditional branch. So for this one, it always changes the PC, goes to somewhere, goes to a new PC. The third is called trap. So the trap is a spatial one. It allows us actually working at the low level to interact with the operating systems. So when we call operating system services, it's called a service routine. It changes the PC to the address of a service routine. And after the service routine is done, it will return the control. OS system, actually, operating system will return the control, means return the PC to the next instruction. So this is 3 types of control instructions. We talked about the controller branches. This one, right?
Yeah.
Yeah, we have.
So a condition is specified by 3 types of 3 bits, right? So the lowercase NZP. So for if n, you can set n equals 1. So this is to test what the value written into the general purpose register is negative. So if it's z set to be 1, this is to test the value written into the general purpose register is 0. So for the p is set to 1, this is to test the value written into the general purpose register is positive. So there are 3 condition bits in lowercase NZP. So they are lowercase, not the capital uppercase. LC3 also uses 3 condition curves. So they are uppercase NZP. NZP here, actually, they are 1-bit register, right? This is to show the value written into a general purpose register is negative, 0, or positive, right? So they are automatically set by any instructions that can allot the value to a general purpose register. These instructions includes like the ADD, AND, NOT, or these operate instructions, and also LD, LDI, LDR, LEA, or these load instructions. Why? Because these instructions, its destination register, they have the destination registers. Do you remember? Right? So at each time, only one condition code is set to be 1. The rest are set to be 0. Right? This is because the value can only be negative, 0, or positive at a time. So for the conditional branches, its operation actually is to test first you need to set the condition NZP here. What condition you want to set here? NZP. And then what is the new PC? Where to, if the condition is satisfied, where to go? The PC, the new PC, change to a new PC. What is new PC? The new PC actually is current, it's a PC offset-based addressing model. So it's PC plus PC offset, right? So this is the new PC. When we say, okay, one condition is satisfied, what does that mean? It means the condition and the condition code, at least one, they have here equals 1. So this means the condition is met. So this is the data path of executing this instruction. Here we have the and also OR. So here, the result here is the condition is his output is 0 or 1. If it's 0, means the condition is not satisfied. So if it's 1, the condition here is satisfied. If the condition is satisfied, then keyword goes to here, and a new PC will be travel through this controller and then send the value to this PC. Then it's new PC. If it's not, then it will go the PC. Here is PC plus 1. Then will go here and go to the PC. So this means it will sequentially executing the instructions. So for the conditional branches, for its instruction cycle, it also has the fetch and decoder phases as all other instructions, right? So, and it's the same. At the fetch phase, the PC incremented by 1, and at the evaluation address phase is to compute the PC and the new PC. So using the PC offset just model. So for the execute phase, the condition codes here, so are exempt, right, or checked, or test. So for example, if you set n equals 1, so this means you want to check n because z and p are 0. So this means 0 and with any number, then the result is 0, right? So this means you want to check the capital N condition code. So if the condition code condition is met, the branch is taken here. This is the branch, the new PC. So if not, then that is the PC. So if all 3 bits NZP, lowercase NZP of instructions are set to be 1, so the branch is always taken because at least 1 condition code is equal to be 1. So the condition is always satisfied. So this actually is a unconditional branch. So this is the branch. Last time we stopped here. Do you remember?
Yeah.
Yeah, I just go review all the materials because 2 weeks, it's 2 weeks now. So maybe you get lost it. So for this example 1, here is if n is 0, capital Z is 1. So this means you want to test Z condition code, right? And the P is 0. Right? And the current PC is X4027. Then at this time, when you run the instruction, the branch instruction, right? This 000 means this is a branch branch instruction, and it tests Z. So let's see the instruction here. The Z here is set to lowercase z, is set to be 1. So this is the condition, right? And then the rest is the PC offset. So here is the condition is 1, and the keys condition code is also 1. So this means the condition is satisfied, right? Because here lowercase z equals 1 and capital Z also 1. So this means that condition is satisfied. Okay, so when the condition is satisfied, this means a branch is taken. So we need to calculate the new PC. How to calculate the new PC? The new PC here is the current PC is right? This is a current one for this instruction. So after the fetch phase, the PC changed to 4027 plus 1, right? And then use this one to calculate the new PC. This is the PC offset, right? So this is a new PC offset. It's 00D9, right? And then you can have the result. So this is the one. So for the second one is here, the instruction is 00 and 111. The lowercase NZPs are all set to be 1. So this means this is an unconditional branch. It will go to a branch. The new PC here is also kids PC for this instruction is 507B. So after the fetch phase, he'll increment it by 1, and then find his PC offset. His PC offset here, right? This one, this is a sign bit. The sign bit is 1, so you need to extend the sign bit. So the sign bit 1 means okay, that is all FF, right? And then here is 8, and here is 5. So this is, then you can calculate the value. This is the new PC. So for the exam 3,
Can I ask a question about example 2?
okay.
Why would you have a branch if everything is going to pass it? Because it's unconditional, I understand that.
Mhm.
But why even have a branch in the first place then?
For this one is, it's like the jump. It always goes to somewhere.
So it's just to move the PC somewhere?
Yeah, the PC is the new piece here. This one is the new PC. It will unconditionally go to this new PC. So for this instruction, so in the next question here, we will you will see here. Okay, sometimes we need to do like the unconditional. For example, here, this one is after you finish the all the functions in this box, it will unconditionally go back to this line, right? And also do the check R2 is 0, the value stored at the R2 is 0 or not. So we have that, we can use in this unconditional branch instruction to do that.
Okay, I see. Thank you.
Or you can use in the jump. We will talk later.
Okay, thank you.
So for the example 3, is capital N is set to be 1, right? So this means the value is negative. So let's see the instruction. The instruction here is, okay, the lowercase n is 1. Okay, so this means the instruction wants to test the condition that the value is negative or not. So they are all ones, so means the condition is satisfied. So let's see his new PC. The PC for this one is, for this instruction is for this instruction x33 x3000, right? So after the fetch phase is 3001, and then the rest 9 bits is all ones. The all ones means they is for the decimal is -1, right? So the result, the new PC actually is still x3000. So for this one, it's we can call it's a deadlock, right? So this is, it will always run this instruction. So this is, it's the simple example for the branch instruction. So do you have any questions? Okay, if no new question, then we will go to the next question, next example. So for this one is to compute sum of 12 integers. These integers sequential stored at the memory, and the first location to store a number is 3100. So, and the program starts at location x300. Okay, so for this one is to solve this problem, we need to first think about the algorithm and draw the flow chart. So for the flow chart here, we have this this flow chart. We're using the R2 to store the 12 as the counter, right? And see whether the number stored in the R2 is 0, right? So if it's not 0, then we will do the sum operation, right? So for the first one, for this one, is to load the first location to the register. So how to put the address into R1? Do you remember? Have any clue?
Load.
Load, yeah.
Yeah, load. So how to load? I mean, how to load?
You use the load instruction, right?
Which instruction?
LD.
No, LD. LD is used to load the data stored at a memory location. For example, here, X3100 into a destination register.
Oh, okay.
Is it a load effective address, which is LEA?
Correct. Yes. So, so for this one is we have to using the LEA instruction. So LEA is 00. So the destination is R1, means 001, right? And then this is the PC offset, right? So for this case, the PC, we know the current PC and the memory location you want to reach X3100. So the PC here at after the please remember that is very important. The PC at the fetch phase is incremented. So here the PC actually is 331. It's not 3000. Do the PC offset, and then should be equal to, right? So you need to calculate the PC offset here. The PC offset here is you right? So for this one, you need to take in two's complement and find the result. And then you can find actually the piece here is, if it's the PC offset is 0, 1, 1, 1, 8 ones. So this is the one. Okay. So then we have the this first instruction. The second one is to do the clean, right? How to do the clean? We can use in the AND instruction, right? For AND instruction, it's 0, 1, 0, 1. So the destination is R3, is 0, 1, 1. And then its source is also 0, 1, 1. And this one is the one using the immediate address model, right? So the last 5 is all zeros. So this is the one, right? To clean the R3. So for the third line, the integer number 12 stored into a register. Here is we can use in the AND addition. It's not AND, addition, add. So add is 0, 0, 0, 1, right? And his instruction register is so for this one, it's also using the immediate model. And then here is the desk number 12. 12 is 8 plus 4. So this means 0, 1, 2. So this is the number here, 12. So this is the first block. So the second block is what? The second block is R2 equals 0, the condition, right? How to set this one? We have branch conditional branch instruction BR, right? So BR is first 0, 0, 0, right? And then it's 0. This is R2, so it's this equals 0 means the Z, lowercase z, equals 0 or not, right? Lowercase z is set to be 1. So this is to check the condition. And then the rest is PC offset. Here, this one is currently you don't know where to go. So we leave the PC offset like here. Okay. So far, do you have any questions?
Yes. So how would it know? How would the program know which register to check?
Okay. So here is R2 equals 0, right? So for the condition code, so the instruction can, here is R2. So the last instruction here should be R2, here R2, and also here should be R2, because these are all can change the value of the general purpose registers. Do you have, I'm not sure this is clear or not.
So the branch just looks at the last like register that was changed.
It's the last, it's not, cannot say last, it's the last instruction that allows the general purpose register. You may have another one like, for example, here, sometimes you have ST or ST family instruction, STR, STR, but these cannot change the value of the general purpose registers. So they can be put here.
And R2 would still be read after the value that was just changed would still be in the general
Yes.
register because it hasn't been changed.
Yeah, that is not changed.
Okay, thank you.
So this is the, this one actually is the difficult part, because sometimes you don't know, based on that branch instruction, you don't know that. You don't know R2, right? So actually it depends on the last instructions. So when you design this, so for example here, you cannot change the sequence here, R3 and R2, and also sequence here. You cannot change the sequence because this one, if you change the sequence, for example here, then the last one is R3. R3 is set 0, then the it's not, this one is not R2 equals 0 or not. This one should be R3 equals 0 or not. So you cannot change the sequence, okay? So this means this is tightly depending on the sequence of the instruction. Okay, after this one, after branch, okay, we have third blocks. The third blocks is first is the data stored at the R1, the memory location, stored in the R1. We need to go to that memory location to load the data into the R4, right? So this is the meaning of the this one. So how to do the load? Which instruction? We have
You just use regular load, right?
Yes. So but which one? For load we have LD, LDI, LDR. So which one?
LD?
LDI, LDR. Why? The LDR is base offset addressing modeling.
We used LEA to get
You
an address and a register.
You have input the memory location into a base register, right? So that's why we use LDR. Okay. So for this one is the LDR is zero, 1, 1, 0. So his destination is R4, R0, 0, right? And then that is the base. Next is the base. Base is R1, right? 0, 0, 1. Then that is the offset. Because you have input the address, the exact address into the R1. So the offset here actually is 0. Right? So this is the one, first line. So for this second line is R3 plus R4. So this is a add instruction. And it has 2 registers for 2 operands. So this is not an immediate adjustment model. So 0, 0, 0, 1. So the destination is R3, R3 1, 0, 0, 1, 1. And the 1 operand is R3, 0, 1, 1. So the other one, so the last one is R4. So R4 is, right? So this is the instruction of the second line. So the third line is increment by 1. So also ADD, right? But it's an immediate model. So this is the R1, 0, 0, 1, 0, 0, 1, immediate model 1. The last 5 bit is 1. So it's 0, 0, 0, 0, 1. So this is the, so this is this one. And for this one, it's the same, ADD. So it's R2. So this is 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1. And this is the minus 1. Minus 1 is F, right? So that is the all ones. So this is the instruction of or the program that can achieve this function, compute sum of 12 integers. So you can see the programs here. You know, after that, after you finish the functions here, you need to go back to the R2, the condition block to check whether R2 is 0 or not, right? So for this one, this is an unconditional one. Each time after you finish this, you will go to this condition box to check. So that's why we have branch 0, 0, 0, right? So for this line, actually. And that is the unconditional. So NZP are all set to be 1. And then the PC offset. So this is the one. So we can go to the this program. So first, for this one, is the piece offset we have calculated, right? That is the decimal number is 255. And for this one is, okay, you need to go to, so if this one is, this is for this line, if this condition is met, is satisfied, then for this one is, okay, you go to like the stop. So for that is go to this line. So this is the PC X3004. After executing this instruction, then that is the PC is 3005. And this one is 3008. That is 10 actually. So 10 minus 5. Then we have that's number 5 here. So for this one is unconditionally go back to here to check. So that is the minus 6, right? So because he needs to go back to here to check whether RC is R2 is equals to zero or not. So this is why it's minus 6. It's because his current PC actually is 300A, right? After executing this one, and then after that, then you'll go back to here. Okay, so this is the, I have write down everything here. Then you can go through this, okay, after the class. So let's see the second example. The second one is very, very similar to the first one. It takes 10 numbers that are stored in memory location also at x3100 through 3109 and add them together. So also do the sum and leave the result in R1. And also program starts at x3000. So they are the same. But if we design a different algorithm, and it may have some difference. So this is the example here. So for this flow chart, you can see from this, for the first block, it's first clean the R1 and then set the 10 numbers into R4 and then set the number, set the memory location, directly set the memory location into R2 here, right? So this is the initialization part. So after that, so for this one, clean, so use the AND. So this is the one. So this one is 001 and 001 and 1, right? So all 00. So this is the one. So for second is also ADD, right? We have learned it. So right, and R4, and that is the immediate, and then decimal number 10. 10 is, you can calculate it as 2, right? So 0, 1, 0, 1, 0, right? So this is the 2, that's number 10. So the third line is to input the number x3100 into the R2. Okay, so for this one, directly using the LEA, or if you know that, then you can write down, if you remember that from our last one. So it's the destination is R2, so 0, 1, 2, 0, and then that is the PC offset here. So this is the first block. So then for the second block, here is not first goes to the condition check block. Here this goes to the function block. This block. So this block is first using the same thing, right? Load the data stored at the x3100 into a register. Here is register R3, so LDR. Right? LDR here is 0110. The destination is R3, 011, and then the R2 is the base register, 0, 1, 0. So then you have the PC offset. Because the this X3100 is the exact mem location, then this is, you can use that's the number to represent is 0. So this is the first line of the second block. So for the second line is to the add operation, ADD, right? It's add the value stored at R1 and R3, and then put the result into R1. So here is 001, and then the destination R1 001, and then one resource is 001, and then this is not an immediate just model. So this is 0, then 20 following, and then R3. Right? So this is the instruction. So for this one is to do the increment. So also using the ADD, we have learned it, right? So this is one. So this is 0, 1, 0, 0, 1, 0, 1, and then this is the decimal number 1. So for this one is last one here is also ADD. So 0, 0, 1, 0, okay, 1, 0, 0, R4, and 1, 0, 0, and then that is the decimal number minus 1. So after that, notice here, here is the last one is R4, not R2, R1, right? So that's why we can check the condition R4 here. So it shows whether the R4 is positive, the value stored at R4 is positive. Okay, so this is a branch, right? The branch here is 0, 0, 0, 0, and is a positive NZP, NZ0, P is 1. So this is the 1, and then the PC offset. So his PC, if this is correct, he will go where? Go to where? It will go to here, right? If it's yes, then that is his new PC. Then you based on this one, his current PC, and the one, the PC for this one. Then you can calculate the PC offset. Then you find the answer. And if it's not, so it's no, then it will stop this programming. Right? So this is the one. So here you cannot see the unconditionally goes to somewhere, right? For the that is the first example has, but this one doesn't have. So this is total based on the everything you design. Okay, so for this one, do you have any questions?
Nope.
Okay, so let's go to, so I have these here, and you can go over. So for the third one is to compute a product of two integers, A multiplied by B, and the result is P. So A and B are two complement numbers. So B is positive, and A and B are stored at the mem location X3010, 3011, and the result will be stored at X3012, and the program starts as X3000. So, so for this one, so you need to think about how to do the multiplication. A times B equals, okay, A times B equals A plus A plus A plus A. How many A's? B A's, right? So this, then we can using the same process to do the calculation. Right? So for this one, it's a bit different from the previous two examples. The first needs to load the data into the memory, from the memory to the register here. Right? So here is, we can use LD. It's a simple, load the data into it. So for this one is 0, 0, 1, 0. And his destination is R0, 0, 0, 0. And then PC offset. So for the, it specifies the destination X3010, right? So the current PC plus PC offset needs to equal to X3010. The current PC is 001, right? So we can directly find out the answer. This means actually, if it's decimal, it's 16, right? So for this one, it's 1, so minus 1, so it's 15. Right? So second is the same, so 0010. His destination is R1, so 001, and then PC offset. So the third line here is to clean the register R2. So to the clean is 001 and operation is R2 010 010. So this is the you have to use in 0 to clean, right? So this is immediate model 1, and then the rest 5 bits is 0. So this is so that second block here is R2. So this is to do the add operation. The result stored into R2 and R0, right? The two source registers. So this is add. So 0001, his destination is R2, 010, and then one source is 010, and the other source here is not immediate, so 00, and then the last 5 is R0, also 000, right? So this is the first line. So the second line here is the same, is to do the decrement. So decrement is also using the add. So 0001, this is the R1, 001, 001, 1, and the rest is the -1. So that is the function here. And then, because the last one is the R1, so the condition code changed based on the value stored at R1, right? So here is check whether the value is positive. So the branch here is 0, 0, 0. Then it's positive. Okay, NG P set to be 1, and then the PC offset. So if this one is correct, it will directly go to here, right, to next instruction. If it's not, it will goes to here. We need to here is need to change, right? So for this one and this one need to change. Here is yes, here is not, right? So if this one is yes, then we'll go back to here. And if it's not, that means you have done all the addition operation. Then you have the result. The result will be written into a memory location x3012. So here is, it's a simple one. We can use it, for this one, we can using ST. So for the ST is 0011. His source is R2 012, and then PC offset. Okay, so for this one, do you have any questions?
Nope, looks good.
Okay. So have the programs here, then you can go over. And because currently I did not write down the analysis line by line as the previous two. So you need to think about by yourself. So for the another type of branch instruction is called unconditional branches jump. The jump is load the PC with the contents of the register specified. So this, what does this mean? So let's see his format. The opcode is 1100, right? So it has a base register here. The base register is to store the PC, the new PC, right? So this one is used to store the PC, which after executing this jump instruction, which location jump to or go to. So this one is used to store the memory location. Okay, this is the jump. Jump is very simple. Directly goes to somewhere specified by the base register. So you can see the data path of executing this instruction. Right? The base register here is his values directly goes to the PC. And you can see this example here. So the value, for example, here, after you executing this instruction, the value x4000 stored at R7 is directly goes to the PC. So this means the sequence will start at x4000 after executing this instruction. So for the jump instruction, because the memory location is written into the base register, so actually has no limitation. For the branch based, it has. So it depends on the PC offset, right? It has 9 bits, so it limited it. Limited the new PC should be within the minus 256 to 255. Right? So this is a unconditional branches instruction. So the third type is called trap. So this one is to let you or let the low level programming to interact with the operating system, because operating system is up atop of the like the assembly and all called instruction architecture SA. So between these two levels, it provides you the interface to do the interaction between these two levels. So for the trap, it's specify the instruction specify the vectors, trap vector called trap vector. So the trap vector actually specify the what kind of service to call, what operating system service to call. And this one is also called service routine. So here is the one, trap vector. So this one is the specify the service routine. And this is the opcode. So the service vector is actually a service vector table. For example, here you have a programming, right? User program. For example, here you have a trap instruction. So first, it depends on the trap vector to go to the trap vector table to find out. Here is x25 here. Then that's a table here. This one is specified the address, starting address of the service routine. Okay, so first, what goes to here to look up the table and find out the starting address. So the starting address here will be sent to the PC. So do you know this was sent to the PC? Then the programming will give up his control and turn over to the operating system. So the operating system will run this service routine. So after the operating system finish the service routine, it has an instruction called RET. Then that you go back to the user program. So here is operating system OS. Here is the user program. So that after the operating system finish the service routine, it will go back to the user program, and then the piece using the RET. RET7 is actually to put the value stored at the R7 to the PC. So this means the PC now, the user program has the PC then to run the next instruction. Okay, so for the trap, do you have any questions?
How do we need to memorize like the different? Do we need to memorize the different trap vector? Like how many trap vectors
Yes,
should we know about?
Currently, you only need to remember 3.
Okay.
X23, X21, X25. So for this one is to using to input a character from the keyboard. This one is output a character to the monitor. So chapter 8 we have I/O operations, and chapter 9 we have the service routine and the subroutine. So you only need to remember 3 or 5.
Okay, thank you.
So this one is this is the process. So when the user executing this trap instruction, he will first goes to the trap vector table to look up the starting address of the service routine it wants or specified by the trap vector. And then the operating system will run this service routine to find the answer. And then using the RET instruction to give back the control to the user's program, and then run the rest instructions. So this is trap. So we have an example. So this example is to count the occurrence of a collector in a file. So you can read it. So this is the process based on my previous explanation. Then you can write down, actually you can write down everything here. For example, this one to do the clean, right? R2 equals 0, means it's a clean R2. And this one is to point to the file characters, right? So I need to use specify the this is a memory address, and then based on this address, then you can find his data. Actually, it's a collector. The data is a collector of this file, the first one. So and then you input a collector from the keyboard. So this one is using the trap X23. This means input a collector from the keyboard, and then load jar from the file, and then you have it one by one loaded from the file, right? So, but you need to check whether it reaches the end of this file. So how to check? EOT is sentinel. That is specified. Say, okay, this is the end of the file. And then if it's yes, then that's it. You have done everything. If it's not, then you need to do the matching. See the value, input value. This one from the keyboard, right? And this one is from the R0. R0 is the return result from the trap. It's automatically stored in R0. So you compare them if they are the same. So how to compare where they are the same? So last time we have, here is the same. You need to take 2's complement and then do the addition to see whether the result is 0 or not. Then if it's yes, then you increment the counter, see, okay, we have one occurrence character. If it's not, then it goes to load another character from the file, right? And then to see, okay, this one is the end, and then go back this loop process. After that, then you need to, because it's called, ask you to print the collector to the monitor. So you have to using this number x30 2 plus the number. For example, here if it's 8, because the 8 it's asking you to click to print the x2 character. So the 8 is x3 8. x2 number 8 is x3 8. That's why we have x30 here. Then print out. The print out is trap x20. It's output the character to the monitor. Then if you have done all this, then it's stop this program. So this is the one, and this is the program. So okay, today we stop here. So you go through this program. Okay, it's okay. Okay, today we stop here. Okay, if you don't have any questions.
No questions, thank you.
Okay.